Hello and welcome back. Today I want to continue talking about antennas by looking at one of the simplest ones that you can build when you require circular polarization. The axial mode helical antenna. A structure which is just a wire, but it's wound in a helix. Looks pretty nice though. Now, before starting off, I just want to highlight that the helical antenna can be used in multiple operating modes, one of them being normal mode. So this is your typical rubber ducky antenna. Here, the dimensions are small in comparison to the wavelength, and radiation is perpendicular to the antenna axis, and the polarization is linear. We can see this quite clearly in the simulator. So the radiation is going to the sides of the antenna. Now the other operating mode is axial mode, when the antenna dimensions are proportional to the wavelength. So we can reuse our previous simulation, just increase the frequency by a bit. Now, I'm not sure how well this simulator presents circular polarization, but we can still see that the radiation pattern is well axial. The peak gain is in line with the antenna, so it's pointing straight up. Now, although the helical antenna has multiple operating modes, these two, the axial and normal mode, are the most commonly used ones. So let's now look at how such an antenna is designed. Most of the initial research on the structure was performed by Dr. John D. Krause, the inventor of the antenna, and it's documented in his multiple works, one of which being the book titled Antennas, which is available on the Internet Archive. In this book, there's an entire chapter dedicated to this type of antenna, so I won't be going into too many details other than how to actually build it. But if you're curious, this is quite a good read. So the basic helical antenna is built by placing a wire helix above a ground plane reflector. The feed line is unbalanced and supplied in between the wire and the ground plane. The antenna is characterized by a few constructive parameters, so you have the helix diameter, number of turns and turn spacing, and from these you also derive the more used circumference and pitch angle. Finally, you also have the reflector and its diameter. So starting from this basic structure, whenever planning to build such an antenna, you start with your operating frequency, from which you derive the wavelength, and then the various dimensions are mainly wavelength dependent. Both the circumference and the reflector diameter are approximately one wavelength, and the spacing in between the turns is a quarter wavelength, and finally the feed impedance is somewhere around 140 ohms. So you will need to apply some sort of impedance matching technique to get this to your desired value. Now, you can go through all of the calculations by hand, or just use an online calculator like this one. So here, you punch in your desired values, so frequency, number of turns, and then hit calculate. And from this you get the various dimensions that you need to build the structure. With this specific calculator, the impedance matching of the antenna to the feed line is done with a tapered section, and while the calculator also gives the values for this. I also found this other calculator, so if you use this, you will get slightly different results, but this also includes a impedance matching section. So here, it's a cylindrical transmission line. But if you want to use this, then again the dimensions are provided in the calculation sheet. So these are not the only solutions, of course, but these are good starting points if you want to build something like this and don't really know what the values are. Now, when building such an antenna, you also need to keep in mind that the helix needs to be supported somehow. Especially with large structures made from thin wire, the mechanical robustness becomes a problem. So one option is that you can 3D print a support structure. There are countless models online, like this one. But I also saw that pipes can be used as supports, or just some sort of rods. Whatever the case, just keep in mind that the support structure needs to be low dielectric constant and low loss, to not affect the antenna performance too much. Last constructive detail to highlight is the antenna polarization. Since this is circularly polarized, you can have either left-hand or right-hand circular polarization. The difference in between the two is which way the coil is wound. So when looking in the direction of propagation, which for this antenna is forward. So with this particular structure, the coil is turning right way. So this is a right-hand polarized antenna. And well, this other antenna that I have still has the same direction of propagation, so forward, but this time the coil is wound leftwards. So this is a left-hand side polarized antenna. To highlight such an antenna's operation, the first test I want to perform today is the impedance and bandwidth test. So to check with a VNA, what are the properties of the antenna that I built? So I first measured the antenna as is and looked at where the reactance passes through 0 and got around 160 ohms. So it's not exactly what it should be, but it's not too far off. Afterwards, I added a tapered impedance matching section, so this should match the low impedance of the coax to the high impedance of the antenna, and while I also had to do some fine-tuning in the 3D print. So anyway, with the addition of this, we are getting a bit closer to 50, though it's not perfect yet. So we're at about 80 or 90 ohms. But for today, I will leave it as it is. I checked both antennas, the left-hand and the right-hand polarized ones, and they are giving similar results. Now, the other test that I want to do today will also confirm the polarization type. So these antennas were made specifically to work around 1.6 GHz, where, among other things, you have the downlink of the Iridium satellites at around 1.62 GHz. And for these, the signal is known to be right-hand circularly polarized. So I set both antennas facing the sky, and in the SDR program, on one channel we have the left-hand circularly polarized, and on the other the right-hand circularly polarized antennas. So when the left-hand antenna is connected, well, we are getting something, but it's a very weak signal. However, if we switch channels, we get a very clear improvement. So while having the wrong polarization will not completely attenuate your signal, it will provide a significant penalty. So it's always important to check what are the properties of the signal you're working with and build the antenna accordingly. Now, if you do decide to build such an antenna, I did find a few more measures that can be taken to improve the performance, which you might consider. So first off, this is a directional antenna that is pointing forward. This is made a bit more obvious by the fact that there's a reflector at the bottom, but the front-back behavior, as well as the side lobes, can be improved by adding a wall around the reflector, basically turning it into a small cavity. This can be a cylinder or a cone. Typical dimensions that I found for this structure being the following. The reflector has 1 wavelength diameter, and the wall is a half wavelength in height. The second consideration has to do with the standing wave ratio. So this is a pretty wideband antenna to begin with, but this can be further improved by tapering the helix. There are multiple ways to do this, but a relatively simple one involves adding a couple extra turns and tapering these to a smaller diameter. An extreme case, however, is making the whole helix tapered. This gives the widest bandwidth. Finally, if you need more gain, you can add more turns, but this becomes problematic at some point. So a better solution is to build an antenna array. While you can add any number of antennas, a good compromise to keep the size manageable is 4. These can be placed 1.5 wavelengths apart to keep the size compact, but also reduce the impact that one antenna has on the other. In the end, the axial mode helical antenna is a relatively simple structure which can provide quite a high bandwidth and is pretty tolerant to how precisely it's constructed. It can be quite cumbersome when the wavelengths are relatively large, but this sort of antenna has been built by amateurs starting from the 2-meter band and well into the few gigahertz range. So whenever you need circular polarization, the structure should be kept in mind. And with that said, Hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.